Okay, objective number four for hazardous material. That's describing, the classification, the properties of physical hazard materials. So as we ended up with objective number three, we talked about hazardous materials are classified into two major categories, and that's the physical hazard and the health hazard. So we will focus in on the physical hazard for at least all or a portion of objective number four. So physical hazard of materials, we're looking at, the tangible stuff. So materials that burn, accelerate burning, can detonate, or have some sort of deflagration. There are 10 classes of physical hazard materials, and within them, a number of subcategories. Uh, us as inspectors, we need to understand that these subcategories will make a major difference in how we apply the code, um, given once the identification of its volatility or the physical hazards. Uh, these subcategories can also dictate, the classification of the building, occupancy, and the use of the building, um, as we look at it from whether it be the International Building Code or NFPA 400. So here is the categories or a list of hazardous materials, or at least the most common. So you've got, flammable combustible liquids, compressed and liquefied gases, flammable solids and gases, organic peroxides, oxidizers, pyrophorics, water reactive material, explosive blasting agents. Um, if we've had previous hazardous material type of classes, certifications, etc., these categories should not be foreign to you at all. So, but here they're broken down for us to understand, how are we going to start evaluating it. Their model codes, the International Fire Code and the NFPA code, looks at looks at characteristics of materials in these terms to be able to determine adequacy or the level of hazard. So flammable and combustible liquids, this is a good chart here, but the most common class of hazardous material that we'll encounter. Um, Very prevalent and very much we deal with liquids that have the ability to ignite more frequent than any of the other types of liquids that have been already categorized. But a liquid is either classified, it's either flammable or it's combustible. Then we look at how volatile that is. So uh, liquids that are classified as flammable combustible, it's all based on their flash point and boiling point. The flash point is only one of the numbers of properties that need to be evaluated and considered in assessing the overall flammability of hazards of a liquid. So when we look at a class 1A liquid on this chart, uh, we have to have a boiling point that's less than 100 degrees Fahrenheit, and a flammable liquid, the flash point has to be less than 73 degrees Fahrenheit. So when you look at class 1 and class B, 1B, the flash points are evaluated the same way. It's the ability, what's the boiling point, is what really separates the one classification from another. So always remember that the flash point is an indicator of volatility, but it's the boiling point that really determines, how volatile a flammable liquid can be. So the chart goes through all the different flash points to where look at combustible liquids. It has a flash point of 100 to 140 degrees Fahrenheit, and the boiling point is not applicable at all. So a good chart to get familiar with. So regarding flammable and combustible liquids, they don't burn. They don't burn. It's the vapor that they release can be ignited and burned. So uh, the lower the boiling point, the better the opportunity for vapors to be emitted. Um, when we compare that to ordinary combustibles, these liquids exhibit a higher heat release rate. And as a result, fires involving uh, these types of material are they're more difficult to control. So I look at it in terms of volatility. So flammable liquids, the 1As, the 1Bs, are more volatile than most other ordinary combustibles. So when we do have a flammable liquid container or some type of a leak in a vessel, the liquid will evaporate, and depending on the atmospheric temperature and the material itself, but that vapor is what needs to be considered as far as how will that vapor ignite. So it's as when we're looking at inspecting premises, we should be looking to make sure occupants store these liquids, flammable combustible liquids, so that their lower flammable limit is never exceeded. So once you have to determine the volatility and what the range is of ignition, depending on its volatility. Flammable and combustible liquids, they're widely available. They have many uses, for anywhere from fuels for motor vehicles, in food prep. There's lubricants, semiconductor fabrication. We coat things with these types of materials, and we create plastics. So we got the petrochemical. I put a note in there about, hey, what about cannabis extraction? Pretty relevant exposure. And what materials are they using to extract uh, to break down the cannabis plant and using it to uh, extract the THC or whatever those other materials are that they'll use in their production. They're flammable. I think there's like methanol or they use ethanol. And how are they using it and how is that being controlled? Um, uh, because flammable and combustible liquids are so widely available, it's one reason why this class of hazardous materials is the most misused, and it contributes to uh, uh, fire ignition, the expansion of fire, and injury and death. So we just have to, as inspectors, really start breaking down, what is the material and the serious hazards associated with materials that have qualities that can be flammable and or combustible. So um, something that I'll leave you with as far as flammable and combustible liquids. What makes flammable and combustible liquids the most misused? I think we just got done talking about it, but I'll refer you to page 387 of your manual. Take a look at that, review that, and get familiar with the misuse of flammable and combustible liquids. Okay, let's move on to compressed and liquefied gases. Uh, Gases they have numerous uses medically in the industrial arena and research applications. uh, model fire codes that we've adopted or that we use regulate the storage and the use. And the regulations address two major concerns: the physical and health hazards of the stored gas, the design, construction, protection of the compressed gas container or cylinder. So these are some things that we are going to be presented. That's a challenge to evaluate and determine adequacy. The application of the model code provision requires that a flammable compressed gas installation comply with general provisions for compressed gas systems and the material specific provisions for flammable gases. Okay, as far as we look at gases, they're categorized into three groups depending on their physical state and containers under certain temperatures and pressures and their range of boiling points. The three categories are non-liquefied compressed gases, liquefied compressed gases, and dissolved gases. Non-liquefied compressed gases, they're compressed gases that do not liquefy under normal temperatures and pressure, and under pressures as high as 10,000 psig, pounds per square inch gauge. Compressed gases can be liquid if they are cooled below their boiling point temperature, which converts them to a cryogenic fluid. Example of such gases include oxygen, helium, methane, and nitrogen. Liquefied compressed gases, that is, gases that become liquids at ordinary temperatures and pressures from 25 to 600 psig. Um, Liquefied gases are elements or compounds that have boiling points relatively near atmospheric temperatures, ranging from approximately 130 degrees Fahrenheit to 25 to 30 degrees Fahrenheit. Let me correct that. It's a negative 130 degrees Fahrenheit to 25 to 30 degrees Fahrenheit. Liquefied compressed gases, though they would become a solid at low temperatures, used for cryogenic fluids. Rules for liquefied gases limit the maximum amount that can be put into a container to allow space for liquid expansion when ambient temperatures rise. Examples of liquefied compressed gases include anhydrous ammonia, propane, and carbon dioxide. Dissolved gases are gases dissolved when it's placed in a solution with another chemical to stabilize it. Acetylene is assigned to this category. Acetylene is supplied and stored dissolved in acetone, which renders it safe to transport and use with proper precautions. Okay, well, here's one of the review questions. Made it easy for you, but the three categories of gases, non-liquefied, liquefied, compressed, and then your dissolved uh, gases. So uh, keep those categories in mind. So let's talk about cryogenic fluids. It's basically the process of converting gases into liquid form through refrigeration, known as cryogenics. So it's cryogens or liquids. Cryogenic liquids have a boiling point of a negative 130 degrees Fahrenheit. Cryogenic liquids are also known as refrigerated liquids, especially when they are in transit. So there are some common uh, uh, materials or gases that are liquefied that are used in our communities for various reasons. So here are some of the most common gases that are uh, converted to cryogenic liquids. Uh, the nitrogen, oxygen, hydrogen, helium, argon, neon, krypton, xenon, uh, liquefied natural gas, and carbon monoxide. Depending on uh, used in could be manufacturing. We'll see that in the medical area. A lot of different applications, all depending on what they're trying to create and the ability to store more gas in a smaller uh, type of container uh, is one of the reasons why we use we convert them to cryogenic. And that's one of the advantages of the cryogenic liquid is its ability to modify material from the liquid to gas volume ratio. So I could put more product in a in a smaller container, if you will, or larger container, be able to have a larger volume of the material. So for example, 862 volumes of a gaseous oxygen can be liquefied to a single volume by reducing the gas temperature below its boiling point. So you could see the advantage of being able to have uh, more material on hand in the cryogenic state. A cryogenic cylinder of liquid oxygen can hold 12 times more gas than a pressurized cylinder of oxygen. So, besides the savings in storage space and weight they offer, cryogenic liquids are valuable simply because they are extremely cold. For example, liquid nitrogen is used to freeze liquids for emergency pipeline repairs to harden gum-like materials such as plastic and cosmetics before they are ground, and for medical purposes. In essence, the hazard associated with cryogenic liquids uh, are to be put into three categories. You've got the inherent hazards of the particular gas, which may be intensified when it's in its liquid form, high liquid to vapor ratio, and extremely low temperatures. So the inherent hazard of liquid oxygen, that oxidizer in that state means there's more of it if it's there, if it's exposed to some sort of, of fire event. And keep in mind, with the exception of oxygen, all cryogenic liquids are either asphyxiants or toxic. So, as inspectors, when we start doing our evaluation, keep in mind that uh, if the nature of the liquid is hazardous to an occupant, think about the volume, the increased volume, because it is in its liquefied state. So, cryogenic liquids and gases such as hydrogen, methane, liquefied natural gas, and carbon monoxide create a flammability hazard because they can burn or or explode. Hydrogen is very easily ignited and particularly hazardous, forming flammable mixtures with air over a wide range of concentrations. So between that 4% and that 75% by volume. If cryogenic liquids are trapped within a confining space, such as pipe or other container without adequate venting, the liquid's going to vaporize, expand, and cause a violent pressure explosion of of the confined vessel. So, are we starting to think about pressure relief? Yeah. So, uh, so liquid to vapor ratios can create extreme uh, explosive conditions when the product is heated within that confined space. And this situation is particularly true in piping. Uh, we talk about pressure relief. These devices should be installed on every length of pipe between two shutoff valves. So some type of approved device It will relieve pressure if there's a buildup as a result of the nature of the material, or if there's heat or some physical characteristic that's impinging on that on that piping. So all pipes that carry cryogenic liquids have to be designed so they slope up from the container to avoid the possibility of trapping fluids inside them. So they're going to pitch back so that there's no potential of having any type of material that's going to be trapped. So pipes and associated fittings, they have to be manufactured from the following materials. So it's very specific on the types of uh, materials that can carry material. So it's so we're talking stainless steel, aluminum, copper, and a manufactured product called Monal, which is a nickel copper alloy. So depending on the product that's being transferred through the piping, these four materials will be used that are going to be compatible with the gas or the liquefied gas. So because of their extremely low temperatures, all cryogenic liquids can inflict severe burns, um, somewhat similar to frostbite upon contact when it's exposed to skin. When small amounts are spilled on skin, cryogenic liquids tend to move across the flesh quickly. In large amounts, they cling to skin because of their low surface tension. Uh, Inhaling cryogenic gases can severely damage your respiratory system, your tract. The vapors can damage your eyes by causing the water in the eyes to freeze. Um, in situations where exposure to cryogenic liquids is possible, you need to use the proper PPE. Uh, when cryogenic liquids are released into the atmosphere, they will refrigerate any moisture in the air and create a visible fog. Uh, and that fog extends over the entire area that contains the cryogenic vapor. Okay, before we move on to flammable solids and liquids, here's a question for you. What hazards are associated with cryogenic liquids? Take a few minutes and go to page 389 and 390 and kind of review that material, and just trying to get yourself familiar with the hazards presented when we're looking at cryogenic liquids. So flammable solids and gases. Uh, a flammable solid has an instant temperature that's of less than 212 degrees Fahrenheit. According to the International Fire Code, the IFC, flammable solids are any solids other than explosives that are capable of causing a fire through the following actions. So that's friction, absorbing moisture, a spontaneous chemical reaction, and the ability for it to retain heat. A variety of materials are loosely categorized as flammable solids. So there's looking at metal powders, readily combustible solids that ignite by friction, self-reactive materials that undergo a strong exothermic decomposition, meaning it's giving away heat, and explosives that are wetted to suppress their explosive properties. Another type of flammable solid includes spontaneous combusted materials. And that's something that it should be readily identifiable, and should be able to determine that by signage or having to look at the SDS or other types of documents. So when we look at spontaneous combustible materials, we as inspectors need to be familiar with the two primary types. You got pyrophoric materials, which is liquid, solids, or gaseous materials that, even in small quantities and without external ignition sources, can ignite within 5 minutes after coming in contact with air, and then self-heating materials, materials that have the potential to self-heat when they come in contact with air. Another classification includes the dangerous when wet materials. These materials, when they come in contact with water, are likely to become spontaneously flammable or produce flammable or toxic gases. Magnesium phosphate is an example of a dangerous when wet material. Materials such as these must not be stored in locations or in such a manner where they can become combustible or dangerous. So, how do you keep these materials dry in a controlled atmosphere, environmentally controlled atmosphere? Flammable solids that are metals require the placement of a Class D fire extinguisher close to the hazard. Uh, when we look at NFPA 10, NFPA 10, the standard for portable fire extinguisher, you know, we have to be able to understand that as inspectors, understand what those requirements are for not only the extinguisher size, but the travel distance. So that visible and accessible and how much do you need and how far do I have to travel? Additionally, inspectors should consult with the safety data sheets to determine, that's the SDS, to determine the appropriate fire extinguishing agent according to the manufacturer's specification. You just need to understand that from a portable fire extinguisher perspective, that you're getting the right agent or the most effective agent given the type of material that might catch on fire. So in this case, we're looking at flammable solids. Flammable gases can be compressed, liquefied, compressed, or dissolved. Examples that would include is ethane, hydrogen, isobutane, and propane. NFPA 55 and the IFC classify gas as a flammable when it meets either of the following conditions. It is ignitable at atmospheric pressure when in a mixture of 13% or less by volume in air. It has a flammable range of at least 12% in air at atmospheric pressure, regardless of its lower limit. All right, the next material, we're talking organic peroxides, but before we get into that, uh, let's do a review question. And what actions can make flammable solids capable of causing a fire? If you take a few minutes, go to page 390 and 391 to review the volatility, the hazards of flammable solids. And that's, again, page 390 and 391. All right, organic peroxides. They only exist only as a solid or liquid. They release energy in the form of heat and are used to introduce energy into chemical reactions so more useful compounds can be created. You know, two-part solutions, you need to add the two together to make a reaction is the most common, at least something that it was always familiar to me. Uh, Two by themselves are relatively inert until they're combined. Um, they present a fire and uh, a reactivity hazard. That degree of hazard depends on the classification of the material. So as they react, all organic peroxides exhibit one or all of the following hazards. They're sensitive to heat. They release heat when they start to decompose. They form free radicals when they start decomposing. Um, and the introduction of a contaminant can initiate an uncontrollable reaction, and decomposition products can be flammable or toxic. So when they start reacting, depending on the material, um, the volatility can be pretty dramatic and varies. All organic peroxides they have a shelf life, and it's usually 1 year or less. Shelf life can be reduced if the recommended temperature limits are not maintained. So they start decomposing if the room that they're stored in, the area that they're stored in, is not environmentally controlled. So once the shelf life is reached, uh, we're talking about how stable the material is. Uh, so the material needs to be disposed of according to manufacturer's recommendation. Um, and when it starts to, when you do get to its expiration, the manufacturer will deem it as being unstable. So our model codes, they they assign the hazard classes for organic peroxides. The lower the Roman numeral number classification, the greater the decomposition, reactivity, and burning rate hazard the organic peroxide presents. So the lower the Roman numeral number, the more volatile the the uh, the peroxide, the material is. Meaning there has to be more controls, or you're limited to how much you can have. So, if you look at, this is table 10.2, which is found on page 392 of the manual. Spend a few minutes looking at it, but we're looking at anywhere from the most volatile to where we're going to get a, a detonation. Um, it it decomposes rapidly, and when it gets to a point of reaction, it's very violent. So, you know, make yourself familiar with that table. Again, it's on page 392. All right. Before we get into oxidizers and oxidizing gases, a review question. Explain hazard classifications of organic peroxide. We just talked about that table 10.2. Again, go to pages 391 and 392 of the manual and spend a few minutes review it. Get really comfortable with you understanding the different types of classifications. Um, so oxidizers and oxidizing gases. Uh, there's solid and liquid oxidizers, and oxidizing gases do not burn. They accelerate the rate of burning. So we think about oxidizers, they enhance the atmosphere and the ability of materials to burn. Uh, Oxidizers yield oxygen or other chemical compounds that promote or initiate combustion. If an oxidizer is heated or contaminated, it can initiate a self-sustained reaction and can result in an explosion or violent decomposition. Um, Oxidizers can also be corrosive, unstable, um, water reactive, or toxic. So depending on what it is, it can have some very severe volatile characteristics. Um, Fire code compliant storage and use of oxidizers is designed to separate them from incompatible hazardous materials. Oxidizers generally will be separate from any other type of material because of their ability to enhance the burning process. So here's a good example of trying to separate uh, materials that have been considered or categorized as oxidizers. Um, so in this slide, kind of separate from everything else, but oxidizers should never be in contact with any petroleum-based materials because of the reaction, could be immediate and violent. So oxidizers are unique in their naming convention. When inspectors encounter a chemical that ends in the letters ATE, ate, or IT, ite, or if the beginning of the chemical begins with the letters PER, per, the hazardous material is probably an oxidizer. Examples of oxidizers, uh, hydrogen peroxide, calcium hypochlorite, potassium perchlorate, ammonium nitrate, and perchloric acids. Um, those are, it should give you an idea, or you should start thinking about them as being oxidizers. Solid and liquid oxidizers are divided into four hazard categories based on their ability to accelerate burning, their rate of decomposition, and if their decomposition can ignite combustibles, which is Class A materials. The higher the Arabic number rating, the greater the hazard the solid or liquid oxidizer presents. So if you look at table 10.3, when we look at hazard classification 4, we are looking at very volatile, very unstable type of materials, uh, where we're looking at explosive. So you're always looking at anything that's classified as a solid or liquid oxidizer, having a marking as an oxidizer, but also has a classification of one through four. So oxidizing gases, they'll support it and accelerate combustion more than just the air that we breathe. They can exist as compressed or liquefied gases, and oxygen can be converted into an oxidizing cryogenic fluid. Uh, Cryogenic oxygen is commonly used for respiratory therapy. It can be found in home health care liquid oxygen type containers. So again, look at table 10.3, which is on page 393 of your manual, and get familiar with those categories, because it'll be important to be able to understand how volatile uh, the material is versus the ability of being able to make sure that the controls are in place. Okay, before we get into pyrophorics, the question regarding liquid oxidizers, what are the hazard categories of solid and liquid oxidizers based upon? Um, Again, I'll reference you to page 393 of your manual. Take a look at those categories and those characteristics. Make yourself familiar with it, and just understand better that there are different categories based on how the material is going to react. Uh, Pyrophorics, category of solid, liquid, or a gaseous material that can produce a significant physical hazard. Uh, so when we look at a pyrophoric material, it's classified when it autoignites in air at temperatures of 130 degrees Fahrenheit or less. It doesn't need an ignition source, just simply the release of material in an atmosphere where the air or oxygen can cause the autoignition. Reason being, the air contains moisture, and pyrophorics ignite upon releasing in air. Um, some pyrophorics are water reactive. Um, so very unstable, the controls to make sure that the material is used appropriately or stored appropriately is pretty significant. Pyrophorics also commonly present other physical and health hazards, including classifications in International Fire Code and NFPA 400 as toxic or highly toxic. So you have to additionally look at how volatile it is, but also the toxicity. So you may have dual controls in place in order for it to be safe. So while some pyrophoric gases and liquids exist, most pyrophoric materials are solid metals. Some isotopes of plutonium and uranium are pyrophoric, used in the manufacture of semiconductors or the synthesis of certain pharmaceuticals and specialty chemical compounds. Example of some pyrophoric materials include arsine, diborane, silane, and sodium potassium, that's Na-K alloys. Because of their inherent hazards of autoignition, the model codes require automatic sprinkler protection in buildings housing this material. So it's not a matter of thresholds. If it exceeds a certain amount or if it's in a certain building, it needs approved fire sprinkler system if you're going to store these types of materials, classified materials, in your building. So in fact, NFPA 1 and the IFC prohibit the storage or use of any pyrophoric building in an unsprinklered building. In the case of alkali metals such as NaK, or which is sodium potassium, or pyrophoric radioactive isotopes, the application of water can grow and spread the fire. So uh, this is where we start looking at different types of special agents to control and hopefully extinguish fires involving pyrophoric materials. So us as fire inspectors, we may need to seek that technical assistance when evaluating the type of extinguishing material that's needed. That subject matter expert, the someone who has uh, experience in working with these materials, and also how to extinguish or control the materials if there's a fire. So requirements of pyrophoric gases are found in NFPA 55 and NFPA 318, which is the standard for protection of semiconductor fabrication facilities. Model codes also reference the Compressed Gas Association standard G13, which is the storage and handling of silane and silane mixtures. All right, when we look at a review question, name some examples of pyrophoric materials. Again, if you go to, or I should say page 393 of your manual, look at, review that material and get more familiar with it. All right, unstable materials or unstable reactive materials can be solid liquids or gases that can react adversely due to changes in temperature, uh, pressure, mechanical, or thermal shock. So if the environment around the material changes, it also can change the, the, the volatility or make a material more volatile to some adverse reaction. Table 10.4 is going to be a good reference when we're looking at unstable materials. So most oxidizers and organic peroxides are also classified as unstable reactive materials. The stabilizing chemical is called a diluent. If the stabilizing chemical is lost, the material begins to undergo a reaction that can cause a fire or uncontrolled reaction. Unstable materials can be found in the manufacturing of plastics, including expanded foams and urethane compounds. So we're looking at, you know, blowing agents that create foam plastics are commonly classified as unstable and reactive. So plastic workers, the examples of unstable reactive materials include hydrogen peroxide in concentrations that are greater than 52% by weight, ethylene oxide, un, unsaturated polyester resin. Unstable materials are classified based on the type of uncontrolled reaction they are capable of producing and how that reaction can be initiated by changes in temperature or pressure. So looking at the environment of which the material or the process is in. A, a thermal shock that occurs if the material is not cooled at a proper rate during polymerization, excuse me, can produce a reaction. So when we look at table 10.4, and this is on page 395 of your manual, we've got classifications of 1 through 4, um, and the the type of uncontrolled reaction, the temperature and pressure at the time of the uncontrolled reaction, and material sensitive to shock. So we're looking at at quantifying how volatile it can be. One is not volatile at all the way up to 4, where the uncontrolled reaction is an explosion or detonation, and is sensitive to mechanical and thermal shock. So spend some time to take a look at and get yourself familiar with that. So the one question is, what do unstable materials react to? Again, on page 394 of your manual, spend a few moments, take a look at that, get familiar with how unstable materials react, um, and that's on page 394. All right, water reactive materials. We're almost through these categories, so we're getting close to the end of this objective. But water reactive materials, they can react violently or explosively when it comes in contact with moisture or is improperly mixed with water. Uh, our model codes regulate water reactive solids and liquids. And they regulate it by how it should be protected, what's the maximum allowable quantities, and things like that. There are no water reactive gases. Many pyrophoric metals are also water reactive. So examples of water reactive materials include trimethylaluminum. Sorry, I think I totally mispronounced that. Uh, calcium carbide, sulfuric acid, and sodium hydroxide. So these are common water reactive materials, and we look at page 395, table 10.5 model, where it says it's titled Model Fire Code Hazard Classification for Water Reactive Materials. So there's 3 hazard classifications, um, 3 being the most reactive, uh, reacts explosively with water without heat or confinement, all the way down to 1 with it has some reaction, but it's not violent. So it's something that, you know, try to understand when we're looking at water reactive materials, the different classifications, because you're going to be seeing that on your safety data sheets. You may see it on placarding that they'll identify it as water reactive, but give you that number classification. And you need to understand probably relatively quickly if that's uh, uh, how big of a hazard it really is. Okay, we're on to the last category of this objective, and that is explosives and blasting agents. Uh, They're capable of producing a sudden, violent expansion of gases that may be accompanied by a shock or a pressure wave. Uh, Explosives exist in both the solid and liquid states. Uh, Explosive classification systems in the IFC and NFPA 495 is based on the UNDMGC and USDOT regulations. So anybody that knows that UNDMGC, what all that means, you show up for class with telling me what that is. I'll give you something. So all explosive materials that meet that uh, the UND MGC criteria are designated as hazard class 1 materials. Explosives and blasting agents are further categorized based on the type of hazards they present. So on 395, it gives you, it's a review of the states in which explosives and blasting agents exist. So I'd spend a few moments and take a look at that, and that's on page 395.